Okay, so we have this picture, right? We have this, so somewhere we had P and W is a totally normal neighborhood of P. Okay, and so for any 2 points in this totally normal neighborhood, for all Q R element of W, there exists a unique geodesic from Q to R well, this may a priori we haven't shown that it stays inside W, but we can join any 2 points by a unique geodesic. In For any 2 points in W can be joined by a geodesic from Q to R, and which is the shortest length curve so which is the shortest length curve in M from Q to R. Is this clear? Yes?
Yes, sir.
Yes. Yeah, because you have this picture. If I take Q and R, I know that I have a ball in the tangent space at Q, B delta 0, whose image under the exponential map contains W, and the exponential at Q restricted to this ball is a diffeomorphism. So I have a geodesic ball around Q which contains W. So for any point in that geodesic ball that includes R, I know that I can join it to Q by a geodesic, and that geodesic will be the unique shortest length curve in the whole manifold, right? Is this all right? Okay.
Yes.
So now we can prove a theorem that
But W need not be convex, right?
no, we won't need the. You can show that actually one can find convex totally normal neighborhoods, but that takes much more work. So we're not going to do that. All right.
Okay.
You can find the proof in Docarmo. After the proof of this proposition, the proof of convex neighborhoods is also given, but we won't need it really. We won't need it. We won't need it. So the theorem is the following, that if you take say xy are 2 points in M and gamma from AB to M is say piecewise C1 curve from X to Y. So then the theorem says if gamma is globally length minimizing, so that means the length of gamma is equal to the distance between X and Y, which is the infimum of lengths of all curves joining X to Y, then gamma is a geodesic. Then gamma is smooth and is a geodesic. Remember, geodesics we only defined for smooth curves, right? Because they were given by taking the covariant derivative of the tangent vector along the curve. So this is saying that globally length minimizing curves are geodesics. So just this length minimality assumption increases the regularity of the curve. I couldn't hear you, sorry. So just this length minimality assumption increases the regularity of the curve. What is the assumption? Sorry, I can't hear you. Can you come closer to the mic? Yes, close. Length minimality assumption. Or can you type in the chat? I can't hear you. Sorry, I can't hear you.
Yes, sir. Am I now audible?
Yes, now you're audible. I don't know what you did, but just keep doing this. This is fine. Yeah.
Okay, so I'm just saying that only the length minimality assumption is increasing the regularity of the curve.
Correct. So it's sort of a regularity result also. You can think of it that way, but it's more. We're saying that it's a geodesic. We're saying it's a geodesic. Not just smooth, but in fact is a geodesic. I'm saying it's smooth because to define geodesic, you need a smooth curve, right? At least a C1 curve or a C2 curve to define a geodesic, because you have to take two derivatives to define the geodesic. The geodesic equation is a second order equation, right? You have to take two derivatives. You're taking the covariant derivative of the tangent vector, right? So taking the tangent vector is one derivative, taking the covariant derivative is another derivative. So that's two derivatives. So for a geodesic, you need at least a C2 curve to define a geodesic. But I was assuming they're smooth anyway, so you don't have to worry about how many derivatives and so on. But,
Yes.
I mean, geodesics are smooth. Geodesics are smooth. So.
Okay.
Okay, so here the thing is here for the length you only need C1 curves. You don't need C2 curves for the length, because the length you get by just integrating the norm of the tangent vector. So there you just need to take one derivative for a C1 for the length, right? So length makes sense for piecewise C1 curves. Is that clear?
Yes, sir.
Okay, so the point here is that globally length minimizing curves are geodesics.
Yes.
Well, actually, we can show that, in fact, locally length minimizing curves are also geodesics. So, but that will follow from this, because here, if it is locally length minimizing, then it will be globally length minimizing for any two pair of nearby points on the curve, right? For any two pair of nearby points on the curve, it will be globally length minimizing, and then by this result it will be a geodesic. So in fact, so maybe I should say it follows that so maybe I'll write this here as a note, observation. It follows that for gamma, a piecewise C1 curve gamma is locally length minimizing. So that we defined at the beginning of the lecture, what it means to be locally length minimizing. So if and only if gamma is a geodesic. So we have a characterization of geodesics as locally length minimizing curves. So one direction I sort of indicated earlier. So let me just let me say the this forward implication this follows from the theorem from the above theorem. You take x equal to gamma T naught minus epsilon, y equal to gamma T naught plus epsilon, right? Okay. And is this clear, what I'm just saying right now? That if it is locally length minimizing, then it will be a geodesic. Because locally, it's the shortest length curve between 2 points on it, right? So, I mean, that means by this theorem, it is a geodesic, right? Restricted to the interval x, I mean, t naught minus epsilon to t naught plus epsilon. But since t naught was arbitrary and being a geodesic is a local condition, it's given by derivatives. So it's an infinitesimal condition. So therefore, gamma is a geodesic. Is it clear?
Yes, sir.
Yes, sir.
Okay. Now the other direction uses totally normal neighborhoods. So given gamma geodesic, and you take P is equal to gamma T naught, and then you take gamma of T naught minus epsilon to T naught plus epsilon. This is contained inside W, totally normal neighborhood for epsilon small, right? Then we know that inside a totally normal neighborhood, we know that for any 2 points Q here and R here, we know that there is a unique geodesic joining these two, right? Which is a shortest length curve also, because this W is contained inside the geodesic ball around Q, right? So by remarks above, for all ST belonging to T naught minus epsilon to T naught plus epsilon, gamma restricted to ST is equal to unique shortest curve from Q is equal to gamma S to R is equal to gamma T. Is this clear? Yes?
Yes.
Yes.
Okay, so here we're using a totally normal neighborhood. I know in the totally normal neighborhood, any 2 points are joined by a geodesic, and that geodesic is the shortest curve between those 2 points in the whole manifold. So that tells me that gamma restricted to ST is the shortest curve from gamma S to gamma T. In other words, gamma is locally length minimizing. Is this clear? Yeah.
Yes.
So once go ahead. Question? Yeah.
For the third direction, we are using this theorem which we are going to prove it.
Right. We're using the theorem which we're going to, that we're using the theorem only in the forward implication,
Yes.
not in the backward implication. We don't need it in the backward implication.
Yeah.
We don't need it in the backward implication. For the backward implication, remember what the proof is. We need to know that W is contained inside a geodesic ball, right?
Yes, sir.
W is contained inside a geodesic ball around Q. And then we use the theorem that we proved last time in the previous lecture, that inside the geodesic ball with center Q, the geodesic from Q to any point in that ball is the shortest curve in the whole manifold, joining Q to that point. Is it clear?
Yes, sir.
So this uses the theorem that we proved in the previous lecture, and also what we proved today about the existence of totally normal neighborhoods, right? So we're not using this theorem here. We're not using this theorem here. In this implication, that if gamma is a geodesic, then gamma is locally length minimizing. We're using this theorem in the forward direction. If gamma is locally length minimizing, then gamma is a geodesic. Okay? Is it clear now, Bappa?
Yes, sir.
Okay. So let's prove the theorem, right? So proof of theorem. So this is not difficult now. So you let T naught be a point in AB. P is equal to gamma T naught. And W, totally normal neighborhood of P. And epsilon positive such that gamma of T naught minus epsilon to T naught plus epsilon is contained inside W. Okay. And so now you let Q is equal to gamma of T naught minus epsilon. R is equal to gamma of T naught plus epsilon. And let alpha from, say, 0. Oh, I should say gamma. Oh, okay. So right, there's one small correction to this. Then gamma is a piecewise C1 curve, which is so maybe I should make a little piecewise C1 unit speed. I parameterize it so it's unit speed. Piecewise C1. I can always reparameterize, right? So it's unit speed. Unit speed. This end. Unit speed. Curve from X to Y. Yeah, so here I'll also make the same change here. Remember that geodesics have constant speed. So in order to say that a piecewise C1 curve is a geodesic, it should have constant speed, right? So you don't need unit speed, just constant speed. But anyway, so the word curve should be after. Okay, is this all right now? Yes?
Yes, sir.
Okay. So let the distance between Q and R be, say, whatever, some D. Okay. So alpha, so I know I have a geodesic, a unique geodesic from alpha, unique geodesic. Well, okay. So alpha is, so okay, actually it's not exactly unique because on the sphere you can go around and come back and so on. So alpha geodesic from Q to R in geodesic ball around Q. Yeah, this I can say. It's a geodesic in the geodesic ball around Q. Okay. So the picture is the following. I have W here. I have P. And my curve, it's piecewise C1. So I don't know what it looks like. Okay. It could be something like this. So this is gamma, and this is Q, and this is R. And I have this geodesic joining them, alpha. Okay. Now, now the thing is, the length of alpha, we know this is the shortest curve from Q to R, right? So this is less than or equal to the length of gamma restricted to T naught minus epsilon to T naught plus epsilon, right? Because alpha is the shortest curve from Q to R. Alpha is shortest curve from Q to R. But this implies that, and also, and also the length of alpha, on the other hand, it has to be greater than or equal to the length of gamma restricted to T naught minus epsilon to T naught plus epsilon. Because otherwise, if length of alpha is strictly less than length of gamma restricted to T naught minus epsilon to T naught plus epsilon, then we can replace gamma on the interval T naught minus epsilon to T naught plus epsilon by alpha and strictly decrease the length of gamma without changing the endpoints. Which contradicts the fact that gamma is length minimizing. from X to Y. Okay, right? So therefore, is this clear? Is this argument clear?
Yes, sir.
Right? If alpha was shorter than gamma from here, from Q to R, right? If alpha was strictly shorter, then I could just replace this part of gamma by alpha. Then the length of gamma will become strictly shorter, right? It will still be piecewise C1. It will still be piecewise C1 because I'm replacing by a smooth curve in between. And so it will still be piecewise C1, but it will become strictly shorter. Is this clear? That will be a contradiction to gamma being length minimizing from X to Y. Is this clear?
Yes.
Yeah. So therefore, the length of alpha is equal to the length of gamma. And because alpha is the shortest curve from Q to R, the unique shortest curve, we showed that any other such curve with the same length as alpha has to be a reparametrization of alpha, right? So, so length of alpha is equal to length of gamma restricted to T naught minus epsilon to T naught plus epsilon, implies by previous theorem gamma restricted to T naught minus epsilon to T naught plus epsilon is a constant well, it's a reparametrization of alpha. And let me take alpha also to have unit speed, alpha unit speed. And so since and because both gamma and alpha are unit speed, gamma of t is equal to alpha of t plus c. It has to be a constant reparametrization because they're both unit speed for some c and r. So for t belonging to t naught minus I to t plus I, t naught minus epsilon to t naught plus epsilon. For some c and r. So gamma is a geodesic near T naught, hence gamma is a geodesic. So gamma is a geodesic, is a smooth curve, is a smooth geodesic near T naught. Okay, for all T naught in AB. So gamma is a geodesic. Is this clear? Yes?
Yes.
This is okay?
Yes.
All right. Any questions? Any questions about this?
Sir, if the lengths are same, then we can say that the images should be same. That's what you use, right?
Yeah, so they're reparameterizations of each other, right?
Yeah. Yeah.
And then the unit speed, so then it has to be a constant reparameterization, right?
Yes. Yeah. Fine.
So that's why I'm saying gamma t is alpha t plus a constant. The reparameterization function is just a translation on the real axis. T goes to t plus c, right?
Yes.
Because they're both unit speed. That's where I'm using unit speed. Otherwise, you could have, I mean, you can start with some geodesic and you apply some diffeomorphism from R to R to reparameterize it, right? And then it will no longer have constant speed, right? So it won't be a geodesic. It'll be, the image will be the same as the image of a geodesic, but it won't be a geodesic. So,
Yes.
so you need constant speed. Remember, geodesics have constant speed, right? So,
Yes.
so it's no loss of generality to assume that gamma is a geodesic, it has constant speed, right? We're just using that gamma has constant speed. So. Any more questions? Okay, is this all right?
Sir,
Yes.
if I join to geodesic and the point of joining, if it is length minimizing, then it is geodesic.
Aha, right. Yes. So, I mean, if it's a length minimizing near the point of contact, right? So, if you do geodesics, so I mean, if you're joining two geodesics, the only way it's going to be a geodesic is if the tangent vectors are equal. So if I join two like this, if the tangent vectors are not equal here, so this one points like this, and this one points like this. Sorry, a bad picture. Then it won't be a geodesic, right? Because I'll take a totally normal neighborhood of this point and I'll join. I know that these 2 points can be joined by a geodesic, right? In this totally normal neighborhood. And this curve is smooth everywhere, right? So this curve cannot be a geodesic from here to here. It can't be the shortest curve, right? Anyway, geodesic is smooth, so the tangent vectors have to agree. The tangent vectors have to agree.
If the joining curve is locally length minimizing at the point of join.
Yes, then because then the same argument will tell you that the curve from here to here, right, at the point of joining, if this is the shortest curve, then it has to equal the geodesic in the normal, totally normal neighborhood, right? So therefore, it will be a geodesic. The same argument that we're doing here, the same argument that we're doing here, right? Yes, you're right. Yeah. So if you join two curves and it stays locally length minimizing near the point of joining, then it will be a geodesic, right? So, I mean, that's just from the basic, what we proved earlier. It's nothing new. We said that gamma is a geodesic if and only if it is locally length minimizing, right? So what you're saying is if I'm joining two geodesics, then it is locally length minimizing away from the point of joining because each is a geodesic, right?
Yeah.
So then I just have to check locally length minimizing at the point of joining. Then it will be locally length minimizing everywhere, right?
Yeah.
Then by this observation, it is a geodesic, right? Is it clear? So yes, what you're asking is perfectly correct. It's absolutely right. Yeah, it's absolutely right. Yeah.
Also, for any compact connected manifold, we always find geodesic between any 2 points. Is it true?
Right. So we are going to prove this. Yes. So the rest of the class today will be about proving this. For any compact connected manifold, we can always find a geodesic joining them. Yes, correct. So compact manifolds are what are called geodesically complete. So that's going to be our next topic now. So we're going to prove what's called the Hopf-Reno theorem. So all right.
Okay.
So that will give you an answer to that question. Yeah. Any compact connected manifold, any 2 points can be joined by a geodesic and by a globally length minimizing curve. And that globally length minimizing curve will be a geodesic, right? That we've shown right now. Yeah. So the next topic is complete manifolds now. Okay, so we understand geodesics completely now as the locally length minimizing curves in the manifold. All right, they are locally length minimizing. So I mean, so for a geodesic, so for a unit speed geodesic, for all T naught in AB, there exists epsilon positive because it's locally length minimizing, such that the distance between gamma S and gamma T, this is equal to the length of gamma from S to T, and the length, because its unit speed, is just mod S minus T. Right, for all ST belonging to T naught minus epsilon to T naught plus epsilon. Okay. So what does this mean? This means that if I look at my interval AB, then my geodesic here in the manifold so suppose this is my manifold. As always, the only manifold we seem to be drawing is S2. There are lots of other manifolds, but S2 is a good example to look at. So the geodesic is a local isometry, right? Gamma from AB to M is a local isometry. So in other words, a geodesic is the same thing as a local isometry into the manifold. Is this clear? This means in a neighborhood of each point, it is an isometry onto its image here. Okay, globally, it may not be an isometry because, as Utsav was saying, you can go around the sphere and come back to where you started. So then it won't be an isometry any longer, right? Globally. Yes? Is this clear?
Yes, sir.
Okay.
Sir,
Huh.
did we show that this is going to be isometry in the neighborhood?
Sorry?
Did we show that this is an